Next, we're going to look at antiderivatives and the indefinite integral. We're going to start with the antiderivative. Anti meaning opposite of. And so we're thinking here the opposite of a derivative, and that's an excellent definition of this. But to be a little bit more precise, a function capital F is an antiderivative of lowercase f if for all x in the domain, f prime of the big F is equal to the little f, f of x. So literally undoing that derivative or getting us the opposite of the derivative. When I take the derivative of the antiderivative, we get back to the original function. We're trying to expand back out to what was that original function. So let's take an example. Let's find the antiderivative of the function little f of x equals x cubed. So we're going to start off really simple. And so we're looking for that big f of x function so that if I were to take the derivative of this big f of x, we would get back to that little f of x. We're undoing the derivative. So we just have to think about our derivative rules a little bit in reverse here. So if I were to take the derivative of something and get to an x cubed, that means I had to have started with an x to the fourth. If I were to take the derivative of x to the fourth, I'd take the 4, I'd multiply it to the front, so obviously that's not right. We'll fix that in a minute. But then we'd reduce that exponent by 1, and that's where we'd get the x cubed from. So I always start by thinking about the exponent in these polynomial functions. But what we just saw a second ago, there's a problem, because the derivative of this right now would be 4x to the third and not x to the third. So somehow I need to get rid of that 4 that would be sitting in front. I can do that one of two ways. I like to use fractions. So if I had a 1/4 sitting there, well, 4 times 1/4 is just equal to 1 as desired. Or alternatively, we could have also said x to the fourth over 4, essentially dividing off that 4 that we didn't want. X to the fourth over 4, it's the same as just a 1/4 x to the fourth. And so here would be an antiderivative. And really, I used an imprecise term here, but it's going to give us a good opportunity to talk about these antiderivatives. Really what we did here was we didn't find the antiderivative, we found an antiderivative. We found one of many. Because what if I had instead put a plus 1 here? Well, we'd take our 4, we'd multiply it to the front, we'd get an x cubed, and we'd have just the x cubed in front, and then the derivative of the 1 is 0. Perfect, that would have been fine. But what if instead of 1, I'd put a plus 15 here? Well, same idea, this will still give us x cubed. Derivative of this thing would be 0. I could do this all day long. What if I put a negative 15 pi over 3 here? Or over, let's do something that doesn't simplify, over 7. It doesn't matter. As long as there's a constant in this last position, we're going to get the same antiderivative. So what we did is we just found one antiderivative, but sometimes it's useful to find the most general form. Because if we're trying to undo a process, if we think, where is this going to come into play later? If we think about our derivatives position to velocity to acceleration, what if we started with an acceleration equation? We wanted to get back to a velocity equation. Well, that's in essence what we're doing here. We're undoing that derivative to figure out what did the original function look like, or what if I want to undo the original velocity equation to get to the position function. We're undoing that, but we are potentially leaving out a constant, and we don't necessarily know what that is. And so that brings us to the next idea, which is the most general form of the antiderivative. So we say if big F is an antiderivative of f little f, then the most general antiderivative of f is big F of x plus c, where this c is called the arbitrary constant. It's just representing this idea right here that we see that there's any number of constants that we could add that we get back to that same original function. So if we have an antiderivative, right, that antiderivative, there's any number of ways we could write it because these constants could be anything. So to get the most general, we're just going to represent that constant with that letter c. Now when we get to the indefinite integrals in just a little bit, Then we can also refer to that c as a constant of integration, but we'll talk more about that when we get there. Arbitrary constant integration, it's going to be the same idea. This idea right here that there's always a constant back there that when we take the derivative of it, it goes to 0. Now, could that constant have just been 0? Sure, it could have, but we don't know. Let's do a couple examples. Let's find the most general antiderivative. And the last example we did a polynomial function. So this time we'll do a trig function. So let's find the most general antiderivative of f of x equals sine x. So the book gives us a table of antiderivatives, but really the key is we want to be thinking about the opposite of the derivative. And if we can do that, we don't have to just memorize a table. We already know how these things work. And so what we're thinking to ourselves is what function, when I take the derivative of it, do I get sine? We know that cosine and sine go between one another. But what I find 90% of the time is we're very, very comfortable with derivatives. At this point, we're very, very comfortable with derivatives. Finding antiderivatives is new. And so let's just do what we're better at. Let's take this and let's take its derivative. What is the derivative of cosine? It's negative sine. And so to correct that negative, I need to put a negative in front. So now if I take the derivative of this cosine, derivative of cosine is negative sine, well, negative sine turns into a positive. But we're not done yet because we want the most general antiderivatives. So this is where we have to remember to include our plus c. Once we have that plus c on there, now we have the correct answer. Take another example. Let's take g of x to be, let's combine a couple functions this time. So let's take e to the 2x plus 5x minus cosecant squared of x over 2. So we'll just take this bit by bit. And we've renamed the function this time, so the antiderivative will be big G of x. We know that e to the x always is itself, so if we had e to the 2x, the derivative of that would be e to the 2x, but then we do have a chain rule here to think about. So I'm going to think about that chain rule. So we get the e to the 2x, but then we take the derivative of 2x, which is a 2. Well, we don't want a 2 in front, so I'm going to put a 1/2 in front to cancel out with that 2. So now we'd have e to the 2x times 2 times the 1/2 gives me just a 1. The antiderivative of x would be x squared. Again, I'm ignoring the coefficient, just concentrating on the variable. But then now I have to go back and think about the coefficient. So I would end up with a 2x, not a 5x. So I need a 5/2 coefficient. X squared, the derivative of it, we multiply the 2 to the front, that gives us a 5. And then we reduce the exponent by 1, giving us just 1 there. And then finally, the antiderivative of cosecant squared is cotangent. And the angle always has to stay the same because of the chain rule. The inner function always has to stay the same. So the derivative of cotangent x over 2 would be cosecant squared of x over 2, but then here we do have the chain rule. So we'd multiply the 1/2 to the front. Well, we don't want a 1/2 in front. So I'm going to multiply it by a 2 cotangent, because now if I take that 1/2, multiply it to the front, we get just the 1. And then because we want the most general form, I'm going to put that plus c at the back, and there is my antiderivative. So we can do this with any of the functions, any of the rules that we've already learned. We can think about how do we go about undoing them, and then just take the derivative to make sure that you have the correct answer. Like I said before, we're very, very comfortable at taking the derivative. So we know that exponentials stay the same with some minor adjustments here and there based on chain rules, and if it's not a natural exponential, we know how to do logs, we know how to do polynomials. Just think about how to undo those, or where we would have started to get to these derivatives. So that is the idea of an antiderivative, but I said that we're going to look at not only antiderivatives, but also indefinite integrals. So let's talk for a minute about indefinite integrals. Let me go ahead and define it. The indefinite integral of f with respect to x, denoted the integral sign f of x dx, is a collection of all antiderivatives of f. You may also see this defined as the most general form of the antiderivative, but we've seen now that with these antiderivatives, there are actually many different antiderivatives for the same function. So this integral is collecting all of them. We're finding that most general form. You may also see the indefinite integral referred to as the function of finding the antiderivative. And that is true because before we're asking the question, given that we have function f of x, what is big F of x? Here, when we see this integral sign, this is a function telling us to find that antiderivative. So it is in itself the instructions. Now just to go over a couple terms, we have this symbol right here. This symbol here is called the integral sign. The f within that symbol, the f of x, which is lowercase, is called the integrand. And that is, again, when it's inside that integral sign. The x is the variable of integration. And the dx, we already know, dx is the differential. And so we're going to understand that dx a little bit better when we get to a little bit later on. We're going to see another video where I really talk about why that dx is absolutely necessary. But for short term, just think that is what we're being told to integrate with respect to. It's kind of like we had to know what derivative we were taking the which variable we had to take the derivative with respect to, because it can be that we have multiple letters in one equation and we may be integrating with just respect to one or two of those variables. We don't have to integrate with respect to all the variables. Some of the variables might actually be constant, or we might be holding those constant. So the dx is denoting what we are taking the integral with respect to, or what variable we're finding that antiderivative with respect to. So if we understand how to find an antiderivative, this is a very simple process. So let's just take a very easy example. So we have the integral 3x to the fourth dx. And so again, this is the whole problem. We don't need any instructions here. It doesn't need to say find the antiderivative, find the integral. The second I see this symbol, that is indicating that I need to find that antiderivative. So antiderivative of x to the fourth, I know I need an x to the fifth. But if I were to take this derivative right now, I'd have 5x to the fourth, not 3. So I need a 1/5 in front to get rid of the 5 that we just created, but I also need that coefficient of 3, or 3/5 there. 5 times the 3/5 is equal to 3. This isn't done because we need that collection of all antiderivatives, or the most general form of the antiderivatives. And so we need to put that plus c, just like we were doing for the most general form of the antiderivative before. Now that c, we can call it the arbitrary constant. That is still fine. But because we were doing integration, we can also call it the constant of integration. The same idea, right? Both are fine. So as long as we understand that process of finding the derivative, integration, very, very simple. And again, it can be any number of terms. So we could have the integral of 2 to the x plus cosine 5x minus 3 dx. And so 2 to the x, well, that's an exponential, so no, it needs to be 2 to the x. But if we took the derivative of 2 to the x, we'd get 2 to the x natural log of x, and we don't have that natural log. Natural log of 2, rather. So I'm going to divide by the natural log of 2 to get rid of it. So right now, if I took the derivative of this thing, the 1 over natural log of 2 is my coefficient. 2 to the x, the derivative of it is 2 to the x times the natural log of 2, which is going to cancel, so that's fine. Cosine, I know, ties into sine, and the inner function has to stay the same. But if I took the derivative of sine 5x, I'd get cosine 5x. The signs are correct. But then I'd take the derivative of the inner function 5, and so I need a coefficient of 1/5, or I need to divide by that 5 to get rid of it. Then 3 is a constant, so I'm just going to attach the variable back to it. So 3 minus 3x. And once again, I need that plus c, the constant of integration. There would be my answer. And so we're just about done, but there's one other last thing I want to look at in this discussion, which are initial value problems. And so it can be that we need to find an antiderivative, and we have enough information to actually figure out what that c is. So let me type out a problem real quick, and then we'll solve it. So we have the problem, find the equation of the function big F of x if little f of x equals 3x squared plus e to the x if it is known that big F of 0 is equal to 3. So we're looking for that antiderivative, but here we're looking for a very specific antiderivative. There's only going to be one case where we have the function at 0 of a value of 3. So we do need to start with an antiderivative. So we're finding the indefinite integral or the antiderivative. I know the antiderivative of x squared would be x cubed. And if we think about taking the derivative of that, we'd multiply the 3 to the front, 3x squared, perfect. I know the antiderivative of e to the x is just e to the x. But then I need that constant of integration too, so I need that plus c there. But now I have enough information to figure out what that c actually should be. I'm told that if I plug in 0 for my x's, my y value will be equal to 3. So let's do that next. Our function is going to be equal to 3 when we put 0 in for those x values. And so 0 to the third is 0. E to the 0th is 1. So we have 3 equals 1 plus c. And that means that c has to be equal to 2. And so now we can write out exactly what that equation is. I'll put the final answer in green. Our function, big F of x, is going to be equal to x cubed plus e to the x plus the 2 that we just found. We knew what the antiderivative of the 3x squared was. We knew the e to the x. We just didn't know initially what that c value was supposed to be. We thought, hey, there might be a constant. There doesn't have to be. The c may have just been 0. But by plugging in that little bit of extra information, we're able to figure out what that c value should be.